So the last thing about Taylor series is how do we get a handle on the error that you make if you use a Taylor polynomial instead of a Taylor series. In other words, if I only use finitely many of the terms, how far off am I going to be for estimating a particular function? So let's start by writing a Taylor series for cosine x at a equals 3 pi. And then we're going to ask the question, if I use the Taylor polynomial, which is the finite partial sum of the series, for cosine x at a equals 3 pi, so the same one, and I'm going to use that to estimate cosine of 10. So it matters, of course, what value I'm estimating. So if you remember what the picture looks like, if I'm estimating cosine of 20, it's going to be a really different error bound than I'm estimating cosine of 10. So it's important to know what that we're estimating cosine of 10. How many terms will I will be necessary to ensure that absolute value of r sub n. So r sub n is called the remainder term. It's also essentially the error. And we put absolute value because the error in this case could be positive or negative, because we could have an alternating series. And I want that error to be less than or equal to 10 to the negative 7th. So this right here is just a way of saying I want 7 decimal places of accuracy. So what we're going to do is start by writing the Taylor series that I'm talking about here. Let's write the Taylor series for cosine of x at a equals 3 pi. So that would be actually a good warm-up for you to do. So I recommend that you pause and just start by doing this. So go ahead and pause now and do this series. All right, now you get to look at the answer to the series. So first we're going to write out the series. So I'm going to start by looking at f of, we're using a equals 3 pi, so I'm going to do f of 3 pi. I'm going to do f prime of 3 pi, f double prime of 3 pi, f triple prime of 3 pi, and the fourth derivative of 3 pi. So how many of these you want to write out is up to you. It's just a matter of how quickly you get the pattern. Some of you guys probably can sort of see the pattern ahead of time, and that's great. If you can do that, I find it helpful to write out at least a few terms. So this is going to be cosine of 3 pi, because we're estimating cosine of x, and the 3 pi is just the a. So cosine of 3 pi and then negative sine of 3 pi, because the derivative of cosine is negative sine. Remember, I'm not doing the derivative of cosine of 3 pi, because that would be 0. I'm doing the derivative of the cosine of x. So if you want to sort of track the functions, this is cosine x, negative sine x, negative cosine x, sine x, and back to negative cosine x. All right, so those are the functions we're using, and we're just plugging the 3 pi into them. So then this is negative cosine of 3 pi, this is sine of 3 pi, and this is negative cosine of 3 pi. And we need to figure out what those all are using our unit circle. 3 pi is coterminal with pi, therefore we just have negative 1, 0, 1, 0, negative 1. All right, and then we need to get our C sub n's for the Taylor series. So the C sub n is f n of x over n factorial. So just take this number and put it over n factorial. So this is going to be negative 1 over 0 factorial, negative 1, this one's going to be actually 0 over 1 factorial, 1 over 2 factorial, 0 over 3 factorial, and negative 1 over 4 factorial. Then I want to remember that what these take as a term is x minus a to the nth power. So this one's going to be, remembering that the a is 3 pi, this one's going to be x minus 3 pi to the 0 power. Remember, we started with n equals 0 here. X minus 3 pi to the first power, x minus 3 pi to the second power, x minus 3 pi to the third power, and x minus 3 pi to the fourth power. So then we're able to write out, and by the way, some people also might jump straight to the sigma notation from here. I'm not going to. I'm going to start by writing out a few of the terms so that I can get the pattern for the sigma notation. So I have negative 1 times, this is just going to be 1, so I have just negative 1. And then I have a 0 term, and then I have plus 1, x minus 3 pi squared, but it's going to be over 2 factorial. So I'm going to have plus 1 over 2 factorial times this, which I can write as x minus 3 pi squared over 2 factorial, 0 term, and then minus x minus 3 pi to the fourth over 4 factorial. And then now I can clearly see what the pattern is by writing it out this way. And so I can write my summation. So that equals the sum from n equals 0 to infinity. Now, here's a good example of being careful of the alternating excuse me, term. So I know I need to have -1 to some power because my terms are alternating. But what I have to watch for is that the first term is negative, and if I plug in n equals 0, I'm going to get +1. Therefore, this is -1 to the n plus 1. So it's important to watch it, like when you start thinking this -1 term, it could be either n or n plus 1, depending on the first term, whether it's positive or negative. So then I can say, what else have I got here? Well, I've got x minus 3 pi to the 2n over 2n factorial. Oops, that is not right. It's like this, 2n factorial. There you go. It's like that. All right. So the next question is the error question, and we will look at that next.